Hello everyone, it's Mrs Jennison here and I'm an Associate Director for our Grange Academies Trust. Welcome to today's lesson, and in today's lesson we are looking at the conservation of mass. Before we start, could you please turn off any notifications so that you can truly focus on this lesson? It would be really useful if you had a pen and a piece of paper so that you could complete tasks throughout the lesson. And it also could be useful if you had a calculator to hand. Now this lesson is a part of our Mass Matters topic, so we are starting with the conservation of mass. Our challenge for today's lesson is to be able to define the term conservation of mass. And our aspire is to be able to explain an apparent loss of mass in a reaction. So to start, I'd like you to list what you might observe if a chemical reaction has occurred. And a little hint for you is that observe means what might you see, feel or hear. So you may have some suggestions, such as you may see some bubbling, and we typically see bubbling or fizzing when a gas is being produced within that reaction. You may see a colour change, either because a chemical is formed or because an indicator has been added to that reaction for you to see the colour change. You may see glowing or burning, and that's also an indicator that heat is being released. And if you have a thermometer, you may be able to see that the temperature is decreasing or increasing. So now it's time to start thinking about what the term conservation means. I'll just give you a few seconds to think about that, and then we'll have a look at the meaning of this word. So conservation has two meanings if we look at the dictionary definition. The first meaning is prevention of wasteful use of a resource. However, in physics, it is a principle by which the total value of a quantity remains constant in a system. Now that quantity could be energy, mass or momentum. And in today's lesson, we are looking at the conservation of mass. So that means that mass is conserved during chemical reactions, even when we see those changes that we saw earlier on a previous slide. Now, Antoine Lavoisier in 1785 came up with this concept, and he said mass is conserved in reactions. The mass of the reactants is equal to the mass of the products in any reaction. Mean? Well, essentially, in a chemical reaction, no atoms are made or destroyed. They are essentially just rearranged and rebonded in different combinations. So that's why the mass of the reactants will always be equal to the mass of the products, because we've got the same number of atoms involved. We can see this on this slide too. So on the left, we've got the reactants, and that's the chemicals that are going to react together at the start. and we've got one blue atom, one black atom joined together, and then one red atom on its own. And when those react, we form one blue product, and the red and black atoms join together and form a different product. I've got the same number of atoms, so I'm going to have the same mass on either side of this reaction. I'm going to have the same mass of the reactants as is equal to the mass of the products. Now these processes can release or take in energy too, but today we are just looking at the mass involved. So how could this look in context? So if I had 10 grams of my blue reactant and I reacted it with 15 grams of my yellow reactant, I would be able to form 25 grams of my green product. That means by doing that, I've just added my two masses of my reactants together to form the product. So it's time for you guys to have a go at some of these. So I'm going to give you a little bit of time after each one. So here's your first one. I'd like you to calculate the missing mass. Try to show your working when you're doing this. Grams, because 5 grams add 5 grams on my reactants equals 10 grams of my products. So now let's have a go at another one. So what you should have got is 9 grams, because 1 add 8 is 9. So for this example, I want you to have a go at calculating the missing mass of a reactant, and you've been given the mass of your blue reactant and the mass of the product. So have a go at this one, please. Okay, so the answer was 3 grams, because you take the 5 grams away from the products that you formed, and that leaves you with 3 grams for the missing reactant. Have a go at one more. So the answer was 11. So remember, in a chemical reaction, all that you are doing is rearranging the atoms that were there from the beginning. No atoms are being created or destroyed in that reaction. So you can see that on this diagram. I've got 4 blue atoms and 12 white atoms in my reactants. And in my product, I've got 4 blue atoms and 12 white atoms. The mass stays the same. So it's time for a quick quiz on this. It's going to be a multiple choice quiz, and there's going to be 4 different choices for you to choose from. So, atoms cannot be created or A, destroyed, B, shrunk, C, changed, or D, all of the above? And the answer is A, destroyed. Atoms cannot be created or destroyed. Next question. 5 grams of A reacts with 2.5 grams of B. What would be the mass of the products? Would it be A, 5 grams, B, 2.5 grams, C, 8 grams, or D, 7.5 grams? And the answer is D, 7.5 grams. Next one, 10 grams of A reacted with B to produce 22 grams of C. How much B reacted? Was it A, 12 grams, B, 2 grams, C, 32 grams, or D, 10 grams? And the answer was A, 12. So on the screen you can see some equipment. I've got a conical flask with some acid in it, and I've got about 20 grams of marble chips. And all of them chemicals and the equipment they are in have been placed on top of a top pan balance. Now if I added the acid and the marble chips together, so if I put the marble chips into the acid, before their total mass was 150.5 grams. What do you predict the mass of the products to be? And why do you think that? Okay, so you've probably predicted that the mass should be 150.5 grams. And that's because of the law of the conservation of mass that we've just discussed. The mass of the reactants will be equal to the mass of the products. Now what we observe with this reaction is we actually observe something different. And there's a reason for that. So I'm going to insert after this slide a video of that practical being carried out, and you can record some results from that investigation into the table on the screen. So you may want to pause the video now and write down the table so that you can complete it while you're watching the video. In the conical flask, you can see here there is 100 centimetres cubed of hydrochloric acid. I'm going to add calcium carbonate to that acid and a gas will be produced. Now once I add that, I'm going to insert a cotton bung, as that will allow the gas to leave the container but keep any of the reacting contents inside of it. And over the time of that reaction progressing, I'm going to take the mass of the contents every 20 seconds. So now I'm going to add that calcium carbonate and start the stopwatch and my cotton bung. So at the beginning, the mass is 271.99. So here are the results for the investigation. As we can see, there was an observed decrease in mass throughout that investigation. Now, part of the reasoning for that, as said in the video, is because the gas leaves the container. So whilst we are observing a mass decrease, we are losing some of that product as it forms, which is why you have that decrease. Actually, we can even calculate the mass of gas that was released by finding out how much the mass decreased by. So now that you have those results and you've seen that experiment, I'd like you to have a go at completing the following statements to analyse those results. Due to the law of conservation of mass, I expected the mass of the products to. However, my results show that the mass. This can be explained because. And then there's a stretch and challenge question for any of you who finished during that time. Okay, so you should have something along the lines of, due to the law of conservation of mass, I expected the mass of products to be the same as the mass of the reactants. However, my results show that the mass keeps decreasing. This can be explained because one of the products was a gas and it was escaping from the flask. And then the stretch and challenge question, why was cotton wool used instead of a tightly fitted rubber bung? This was so the gas would be able to escape, but no reacting liquid would. If the bung was used, then the gas wouldn't be able to escape, and actually you'd end up with it being fired out of the top at some point. So that's everything from me this lesson, and I will see you soon.